Dr. A.R. Srikrishnan will be handling you access fluent usage, how to use it. Okay. He will also give you important tips. Meanwhile, you can download Access Fluent. There is academic version, academic license, for which you don't have to pay any fee. You say you are a student and you can download the license free of cost. Have it on computer. Only thing is, it will have some limitations on the number of nodes you use. You can't use it for very heavy problems. That's the only limitation. Otherwise, it will have all the features of the normal licenses. Okay. So this is to lay a ground for introduction to CFT. We introduced a little bit. Now we'll go a little bit deeper. Then give a flavor of various terminologies and concepts in CFT. So it's an ocean. If you go inside, there are a lot of things to know. This will hopefully get you started on CFT course. From where, if you're interested, you can pursue an advanced course or learn things on your own. But the basics will be covered here. So now we have seen, wow, we haven't seen the unit. Unit 3 we haven't seen from syllabus. Correct, Sanjay?
Yes, sir, Unit 3.
Yeah, I will just. This is how I get the syllabus. Unit 3 is stability analysis. Von Neumann stability criteria, which means that using this criteria, you can, for a certain class of problems, you can predict whether that FD we have designed. You see, FD is finite difference equation, which is an algebraic approximation of the partial differential equation. Now, using this von Neumann stability criteria, for a certain class of problems, you can predict whether your FD is going to converge or diverge. If it is diverging, there is no point in using the FD. You have to reformulate the PDE in a different way. Some things have to be different. Even before starting any calculation, you can predict that using the stability criteria. If it says it will converge, then there is a high possibility that it will converge. Even then, that can be unforeseen errors. But if it states it will diverge, then almost certainly it will diverge. For this stability analysis. Then we'll also get one CFL criterion for stability. This has some physical reason, but then whatever we cannot explain by that reason, we just multiply, use some scaling factor to reason with the practically observed things. CFL is actually, each letter stands for one great scientist or contributor to CFT. Okay, we'll look at those names later. Then we'll be introduced to the mathematics of grid generation, that is body conforming grids. Then algebraic, what is algebraic grid or elliptic grid? Then some unstructured grid, what are unstructured grid? C grids, O grids, H grids, etc. For flow past airfoils and wheels. So this will be more of practical hands-on experience. Generating the C grid, O grid, H grid. And simulation of external income flow also you'll do it in exercise using answers. Mentioning specifically here. Because instead of answers, you can use other software also, like Open Program, CFX. Right, this assessment is it's a general one, most of the textbook. This is the textbook I'll be following. Okay. John D. Anderson from Basics for Physics. There's also one good book by Hoffman. In fact, there are plenty of books. When the time comes, I will share with you other references. So, in spite of having I thought that we go by this way. So the course will be organized in this way. First, we go to the basic terminologies, then we look at ground information, then mathematical properties of these equation. We know how to classify this, and we should know what is a well-posed problem. For example, a PDE, if you define a problem which needs an initial condition, but you are not giving initial condition, so you are going boundary condition, then the problem cannot be solved satisfactorily. It is not a well-posed. So we should have solvable things. That is, then if the problem is well-posed, we can attempt solving it using numerical techniques. Now, criticization of PDEs to FDEs, that error and stability, and we go after that. Then grid generation, transformation of FDEs from physical space to computation space. Parallelly, we may also be generating grids using analysis. Then we look at some CFD method. The simplest CFD method you might have already used in your vortex panel method or force panel method in earlier instance. We look at some other complicated methods also. Not complicated, say some better methods for other types of problems. Okay, so now we start with the great photo of the great people. These are the founding fathers of fluid mechanics. So we take their blessings before we start. God Louis Navier and Sir George Gabriel Stokes. What are they famous for? For Navier-Stokes equations. Okay. So the correctly formulated equations, which is being used even today. Salutations to them. Let's go on with the course. Now, why do you need CFD? The governing equations of CFD are 5 in number. They're difficult to solve analytically, except for specialized cases, which are not useful most of the time in the industry. So how can we use computers and extract useful information with the equations? We are engineers. We want to do something which is useful. Okay. Unless computers are good at handling discrete numbers rather than formulae. Also, we have numerical analysis, which provides an approach to get approximate solutions to PDEs. Now, the art of extracting useful solutions to fluid dynamic, or in our case, aerodynamic problems from the governing equations using computers and numerical methods is known as computational fluid dynamics. So, this you can say is a sort of definition of fluid dynamics. So, excuse me for a moment. I will be back. Okay, I'm back. Now, what would we learn in this course? So it's good to know the governing equations and their nature. So relevant numerical approaches to solve them. Yeah. Any doubts? Hmm? So we'll be learning about the governing equations first. Something about how to arrange them in a form suitable for CFD. Then we'll also learn some numerical approaches to solve them. Each method may have its own advantages, disadvantages, and some notes of cautions, pitfalls where we should look out for. Okay. Then we should know something about the machines which solve them, how to use them. For example, how do computers affect our calculation? Hmm? And it will be good to know programming because all these numerical methods are programmed in the software which you use, ANSYS Fluent. Now, if you want to extend, if you join ANSYS company, you will be asked to extend that. So you should know program. Okay. Hope all of you would have done some programming in your first year. Yes or no? First year, you have some computers related, program related
Yes,
course.
C program.
C program, yeah, that's good. That's good. How about C++?
So that I learned in 12th standard management.
But generally, in general, I mean, it's not yet taught in the first
No,
year,
sir.
no? Okay, okay. Anyway, it doesn't matter. Some programming knowledge should be there. Let it be Fortran, C, C++, or anything. Nowadays, people are using Python for most of the thing. Okay. Then we should know something about the existing CAD software. Fluent, CFX, OpenFOAM. If you use one, you'll know, the functionality of the other. Then you'll know that, what are the slight differences between how to use them and other things. OpenFOAM is an open source software. You can actually download the source code, modify it according to your wishes, and you can even make the GA look different, but not so with Fluent and CFX. Initially, they were separate companies. Then ANSYS bought out both of these companies. Now they are the same umbrella of ANSYS CFD. ANSYS CFD has both these software, Fluent and CFX. Both these are based on similar methodology. There are small differences between them. So what those who were competitors earlier, today they are offered under the same umbrella for the customer. Whatever you like, you choose, but buy from ANSYS. Okay. Now, how will CFD be useful? Now, we can solve theoretical or practical problems using CFD. It's one more method of verifying your results in case you have a result. It's a third arm to supplement or correlate. That is, supplement in the sense you can solve some problems which are not solvable either analytically or experimentally, or correlate. For example, you get some results, you want some confirmation whether it's correct or not. Then you do CFD and try to confirm it. Correlate analytical and external studies and predictions. Nowadays, wherever you go in designing, aircraft rockets, I don't mean conceptual design. When you go to the preliminary design and detailed design, okay, of aircrafts, rockets, missiles, engines, turbo machinery, windmills, wind turbines, civil and mechanical engineering, atmospheric sciences, oceanography, naval architecture, also even electronics. They even analyze, how to cool the air which is passing through electronic systems. So in so many areas, you find CFD's influence. Okay. So wherever the effects of fluid medium are important, you can find CFD in action. Also, when there is no other way to get your result, CFD is more important when the analytical and experimental studies are difficult, unreliable, or impossible. Okay. Now just have a sneak preview of grids. This should be good enough for you to get started on answers. You'll know how a grid looks like. As told earlier, we get approximate answers only at the grid points or grid centers. Analytical method gives you a continuous functional answer. This is a type of grid called elliptic grid. If you seek for solutions in the domain bounded by the boundaries of this area, inside that and on the domain boundary point, you seek solution only at the points or the intersection of two grids. Okay, so they form this kind of pattern. So this looks pretty smooth. Okay, for some purpose, grid is generated. These are some other grids. These may also look like this. These types of grids are known as Poisson grids. What they have done is, the turbine vane is actually a circular problem. You draw, a circle of radius r from the center of that this arrangement, vane arrangement. What you will see, if you take a section and take it out, you will take a section of aerofoils arranged in a circular fashion. Now the circle is actually cut at some point and opened. When it's opened up, you will find them arranged neatly, one below the other. They are taken only two such airfoils and try to analyze the flow. Okay, this one is called a one period. See, the same grid keeps repeating. So such grids are known as periodic grids. Well, they simplify the actual problem and then try to get some solutions. Okay. So people used to do this. Even now, some people try to solve problems this way. Now, this type of grid is known as C grid. Okay, we'll see why it's called C grid. This is like a C. It's like a C. There are other types of grids. Anyway, just to tell you that the way these grids were generated were using some equations known as Poisson equations. Okay, we all know Laplace equation, correct? What is Laplace equation? Anyone?
So del square of any scalar function is equal to 0.
Who's answering?
Sir,
Yes.
Ramnath.
Ramnathan, yes. Instead of 0, if you have a function of x and y there,
Yes, sir.
either of x or of y, may be a constant, is not 0. If the right side is non-zero,
Yes, sir.
then that is Poisson equation.
Okay, sir.
If you use Laplace equation, you'll
Yes,
get
sir.
grids like this. Okay. We'll later see how to use those to get grids. Okay. If you use Poisson's equations, you can get grids which are clustered in the region you want. For example, here there is more cluster near the body, correct? You may get
Yes,
some
sir.
in this point, it's just a continuation of the clustering. So such grids which use Poisson equations for their generation of grids itself, known as Poisson grids. Now, this is just to get the grids, remember. For the grid generation, we are using Laplace equation or Poisson equation. But what we are solving is the Navier-Stokes equation. Then this is taken just like any other grid. Okay. When you say Laplace and Poisson grids, doesn't mean that you can solve only Laplace equation and Poisson equation on those grids. That's confusion. It go from your mind. It just says
Okay.
that to generate the grid, you use these equations. That's it. Okay. This is an important concept you should know, which is adaptive grids. When adaptive grids are used, the grid changes with the evolving flow structure. during the computation and automatically clusters more points in regions of interest. That is where steep flow gradients are encountered. The example is shown the next one. This is pretty useful for very complicated geometries and supersonic flows where you can't guess, where the flow gradients are going to be. For example, how do you know a location of shock even before calculating the solution? So what if the shock is formed in the area where you have clustered less number of points? Only after looking at the solution you scratch your head. Oh God, I could have put more points there. So I might have got a better solution. So to address such issues, these adaptive grids are used, where after a certain number of iterations, the solution is seen. So the flow gradients in the solution are used to cluster the grids now. Either put more points or redistribute the points in the grid in such a way that near high flow gradients, grid is clustered more. So next slide, you'll see a adaptive grid for projectile penetration problem. So from left to right, you see this is the initial projectile, maybe a bullet. Okay, a bullet is piercing through some box like this. So this is the initial. They expect that there'll be more, more samachar happening here. So they have put a little bit more number of grid points there, and outside they have less number of grid points. So, right, then after some time, they look at how the flow is changing and change the grids. So now when the bullet is passing through, okay, a projectile is passing through, it's a long projectile, as far as I can see. There's some leading edge shock, leading edge development. When they develop, the more clustering is also happening. That's why you see the dark points on the grid. So they have put more number of grid points here also. So the grid points actually look like the solution. Now once it penetrates, there is more something happening here. So points are clustered here. Here you can see some white patches where there are not much gradients. So they have removed some points there. Okay. So it's a very long projectile from here to here. So in the bottom, you will see the solution, that is pressure contours. Okay. So you can see the similarity of the pressure contours with the grid where it is clustered. Okay. So in these areas, you can see there is less number of lines, which means the gradient is less there. And here there are more things, many numbers happening, so automatically it is clustered here. Now, although this looks very attractive, this involves more number of grid points, and it will take more time to generate this solution, because after every few time step you have to generate the grid once more, which is an onerous task. The computer will do it for you, but the time taken to get a solution may not be acceptable in this case. Sometimes, it depends on how much time you have at hand. Any doubts so far from anyone?
Sir, from this example, can you tell how adaptive grid is being used? Sir? In the sense, again, just for clarification.
Yeah. Who is this? Ramanathan?
Yes, sir.
Okay. See, initially, let's say this shows a snapshot only at certain time steps. This process will go on in between time steps also. Okay. Let's for example, we start with this grid. At this point, you have the solution. Solution also you see for every after every 10 iterations, for example. you see the pressure will change, correct? The pressure distribution will change. Everything will change.
Yes.
So based on that, dou P by dou X or dou P by dou Y, wherever the gradients are more, in the near shocks, the gradients will be more, correct? Or near sharp corners or curvature, the gradient will be more.
Yes, sir.
Gradient of flow properties. Gradient means rate of change, right? If it changes two changes, so if there are high changes somewhere, you want to capture all those high changes. Where the gradient is less, it is not changing at a fast rate. So you don't want to put more points there. Okay. So it shows exactly when solution is like this, the grid has also adapted itself to something like this. When solution appears like this, the grid is adapted to something like this. Okay. We see some, not exactly the same picture, but this grid will be similar to the contour you see here. And once it is penetrated, it is better to have this grid because all the regions of dark, there are so many grid points there, you can't make out them at this scale. Why are there so many grid points? Because from the solution, we found out that the change in pressure in that direction is very high. And they somehow implemented that in the grid also. How they do it, we'll look at it later. We'll have a, very first look at it. We won't go into details, but we will go into the initial detail. Okay, Ramanathan, clear now?
Sir, yes, sir. Yes.
Okay. Any other doubts?
Sir, no, sir.
Okay. So unstructured meshes. You should also know what are unstructured meshes. See the grid shape here is rectangular. You have, all the grid is rectangular or square or something. Here also, if you look at an individual cell, it has 4 points, quadrilateral, let's say. So quadrilateral we call rectangle. You can have, x comma y, x comma y. You can redefine every point as, for example, this point on the top, I can say, 0, 1, 2, 3, 4, 5, and suppose it has, 10 numbers, or this is 11th number. I'm calling this 5 comma 9 is this point. 6 comma 9 is this point. 6 comma 8 will be the point below that. Like that, I can assign for every grid point one index, I comma j. Is it clear? This is regular grid. Now I can say, what is the x at 5 comma 9? What is the y at 5 comma 9? The x and y is different. You may have a regular x and y axis. The distance in the x axis y axis can measure for that point. So x at 5 comma 9 can be, say, 1 meter. Y at 5 comma 9 can be 1.8 meters. Like that, I can give the x and y coordinates of each and every point here. The x of I comma j, y of I comma j. Similarly, I can have the velocity components also at every point. U at I comma j, v at I comma j, w at I comma j, p pressure at I comma j, rho density at I comma j, t temperature at I comma j, and whatever else you want. So this is possible if you have a rectangular grid, in the sense that in physically it looks like, as if it is not a rectangle, but we call it rectangular grid. When you do some transformations, you can transform it to a rectangle. This is also, each grid looks nothing like a rectangle, it's quadrilateral, but it's proper transformations. If you can express the I comma j, then you call it as a rectangular grid. The unstructured, these are structured grids. What you see here, structured grids. You can extend it to 3D also. X at I comma j comma k, y at I plus 1 comma j minus 1 comma k plus 2, things like that. You can define. Unstructured measures, you can use even triangles. It doesn't go by the usual I comma j, thing. All points are identified like earlier, okay, but by a different system. Now they look more like triangles in this. In 3D problems, you can have tetrahedra. Instead of triangle, you can also have hexagons or any polyhedra in case of 3D problems. These are commonly employed. The advantage of this unstructured measures is that very complex geometries can be handled satisfactorily. Okay, when you use this structured grid, you have some disadvantage that if the geometry is complex, you will have some numerical errors and some instability, which can be minimized if you use a structured grid. But the kind of control is more in the structured grid, and the control you have of the shape of the grid is less in case of the unstructured grid. Now this schematically shows the pressure contours on what is known as HSCT aeroplane. HSCT is high speed civil transport. So this is post processing. Once they got the numbers and results, they use these pressure at every I comma j comma k here to generate contours like this. From this you see that red is high pressure area, blue is low pressure area on the top. So green is somewhere in between, green and yellow are somewhere in between. Okay. So it looks nice, like low pressure on bottom, high pressure on high pressure on bottom, low pressure on top, probably producing sufficient lift. One more example. This is 2D example. Wind turbine airfoils. So here again, probably pressure is shown here. It can be velocity also. You find high pressure near the stagnation point, red, okay, and low pressure, blue, in the region of high curvature, okay. So we have higher pressure on the bottom, very low pressure on the top, producing lift. Physically reasonable, you get an idea of the pressure distribution, the nearby domain as well. In addition to the airfoil, which is of most interest to us, you also get an idea of how these affect the flow in and around the airfoil. Then this is typical application where you can have CFD. You see, this can never be solved analytically. Never means analytical science has not grown up to this level. CFD is turning on wing external store. There is a wing with external store like a missile or a rocket there. It's called as external store. Again, obviously this will interfere with the aerodynamics to increase drag and reduce lift. By how much? We don't know. That is why we are doing the analysis. We may even do an experiment for this. Now this shows The mesh is now not shown in 3D. It is showing only intersection of the mesh with the solid surface. In 3D, you have something like volumes. Okay, each intersection of these will tell you where the discretized points lie. So correct connectivity will give you a 3D, kind of mesh. Okay, so this shows how the CP and CP varies in the top surface of the wing and bottom surface of the wing, probably at a specified section. Okay, so we all know this area will give you lift, CL actually. Okay, so that's it. Any doubts on this lecture? Any doubts at all?
Image you had showed in the previous.
This one? Is it like?
Yes.
No. Tell me. What is the doubt you have?
So the air
I have lost your
colors
voice.
that share on these. Do these colors have usual fixed meaning?
Can you text to someone because your voice is breaking off?
Sir, he is asking, do the colors have any meaning?
Yes, of course. The earlier colors, yes. Look at the legend on the left. This is blue is low value, red is high value. Okay. Here is pressure contours. Then blue is low pressure area, red is high pressure area. Same way here also. Clear, Sanjay?
Yes, sir. Yes.
Yeah. Did I address your question? Did I address your doubt? Okay, I hope I did. So there's some problem with the connection, your connection. So I'm not hearing what you're saying. Okay, so let's stop here today. Next class we look at some basic definitions and concepts. What is continuum? Lagrangian Euler formulations of the equation. What is control volume? All fluid dynamic stuff. You might have learned fluid dynamics. What is divergence theorem? Then what is the mathematical model? First, we will look at some philosophical statements. Same way, simulation. Then how do you validate results? So all these things we'll cover next class. Okay. Have you recorded?
Yes.
Yes.
Okay. Okay. Is there any doubts you can ask? Otherwise, I will, end the meeting after taking attendance. Last class I forgot to take attendance, but thank you.
Thank you. Thank you.
Thank you, sir. Bye, sir.
Thank you. Bye. Bye.
Thank
See
you,
you on
sir.
Thursday. Yeah. Bye.
Thank you, sir.